All right, chemistry. So we've talked about the quantitative study of some of these gas laws, like Boyle's law, Charles' law, Guy-Lussac's law. We've talked about all those. And Avogadro's law. But in addition to this, those laws are great for making quantitative predictions, like if I increase the temperature, how much will the volume increase or decrease or whatever. Great at making quantitative predictions, but not so good at making qualitative predictions and explaining why those gas laws apply. In order to explain that, using a theory, chemistry uses what's known as kinetic molecular theory. And so I'm going to give you some notes to take because this is one of the key takeaway points of this unit. And so I'm going to open up this thing. It's called kinetic molecular theory. And there are a couple major key things about kinetic molecular theory. So I've got kinetic molecular theory. And remember that kinetic means movement. And so we're talking about movement of particles, and particularly gases. So the kinetic molecular theory explains motion of gases. So if I slide this over here to this part, you can see something particularly about these particles. If you look closely enough at the particles, you'll notice the particles are moving at different speeds. Some are moving faster than others. However, the average of all of those speeds can be indicated by the temperature. Notice it's a constant 300. The average of all the speeds is what's known as the temperature. And if you notice this, as I increase the number of particles or I put more particles in, notice the average speed of those particles do not increase. That's still 300. So, the average of particles are moving, and something becomes very obvious. As I follow these particles around, you quickly begin to see that they are clearly moving and they never stop. So, kinetic molecular theory tenet number 1 is gas particles never stop moving. In fact, I can be a little bit more specific. They move in a linear fashion. What that means is that the particles move in a straight line. If I slide back over here, those particles are moving in a straight line until something happens to them, which we're going to talk about here in just a second. But they're not curving and they're not bending. They're staying in a straight line until they bump into their neighbors. So that's kinetic molecular theory's first key idea, is that all these gas particles are moving. And we know this to be true for liquids and solids as well. That's the first thing. The second thing is what causes them to change from the current state that they're in, which is collisions. And there's a couple things about collisions. First off, there's two big types of collisions. They're called elastic and inelastic, and I'm going to write this stuff down here. Elastic versus inelastic. An elastic collision works like this. Imagine you were to take a bouncy ball and you were to drop it. If it was 100% elastic collision, then what that would mean is wherever I drop the bouncy ball from, it would bounce back up to that height. That means that they completely bounce off of each other. So an elastic collision means that they bounce off of each other and no energy is lost. Now, we haven't talked too much about, oops, didn't mean to cover that up. We didn't talk too much about what energy is, but the key thing is that no energy is lost in an inelastic collision, 100% one. An inelastic collision would be something like if I were to take a piece of Play-Doh and I were to drop it on the ground. That thing's going to smush. It's not going to bounce at all, especially if it's really soft. Imagine that it completely sticks on the floor. What that means is they stick together and energy is lost. In this case, most of the time it's due to sound or things like that. If I slide over here, these particles are moving and colliding, but they are not sticking together, which means that they are colliding with elastic collisions. So the second key tenet is this. Gas particles collide with 100% elastic collisions. This is key because energy is not lost in the process, which means that they bounce off each other! Exclamation point. The third tenet has to do again with the collisions. If I watch these guys, they're bouncing off of each other, and there's a thing that I can look at on here that would indicate how intense these collisions are, and that is not the temperature, but the pressure. If I add more particles, then the pressure is going to increase, causing an increase in the number of particles, just like that. I increase the number of particles, we know that that's directly proportional, which causes an increase in the pressure. That's because the collisions, these particles are not moving any faster, as indicated by the temperature. But the reason this happened is because we're increasing the intensity of, increasing the frequency of collision. There's one more thing that we can do to increase the pressure, and that is we increase the intensity of the collision. That means we make the particles move faster. Imagine two bumper cars that gently bump into each other. That's not much impact. But if I were to take two high-speed cars and ram them into each other, that's going to be a high-speed impact. So, the third main tenet is as follows. Gases collide. Oh, excuse me, I'll change this. Say pressure of the gas is measured by the intensity and frequency of the gas particles. Of the gas particles collisions. Let me make sure I spell that right. Intensity. Boom. So pressure of the gas is measured by the intensity and frequency of the gas particles collision. So the more they collide and the more intense they collide, that's going to cause the pressure to go up. The final thing is, if I were to want to increase the average speed, which I've made a big deal about by pointing out the temperature, the only thing that I could do without affecting other variables would be to increase the heat. And so if I increase the heat, you can see that the temperature is clearly rising. So, the fourth and final main tenet of kinetic molecular theory is that gas particles speed up when heated. And we knew that from a long time before based on discussions we've had in class. But now it's key because this is the major theory that explains why gases move the way they do. So those four main tenets explain kinetic molecular theory, and that is still something that is used in chemistry today. Now, we've got the quantitative understanding by using ratios to make predictions quantitatively. Now we understand the qualitative things behind it. The final thing I want to do before I have you guys do something is I want you guys to consider the following. And I'm going to draw something here on a piece of paper. So if you consider the following, I've got a pressure volume graph. If you remember, those guys are inversely proportional, which means the graph is going to look something like this. If I were to take three different points along here, if I were to consider a point here, and a point here, I call this point 1, point 2, and point 3. What I'm going to ask you to do is this. I'm going to ask you to draw a particle diagram representing part 1, point 2, and point 3. So if I were to draw point 1, I'm going to walk this through for you, and then I'm going to give you an assignment later. If I were to draw point 1, I'm just going to draw a simple little box, and I'm going to draw two particles in there. Boom. And I'm going to actually show the speed of those particles. And so I'm just going to pick randomly. I'm just going to put two lines behind them just to show their medium speed. Now at this thing right here, at this point right here, it has a very low volume. You can see that because it's very close to zero. But it has a very high pressure, which means that these guys are colliding with pretty high frequency. Now number 2 is down here. What I physically did was I lowered the pressure, but that was as a result of increasing my volume. So to show that my volume is increasing, I'm going to physically draw a bigger box. Just like that. This box is clearly bigger than this box. However, it doesn't say anything about me affecting the number of particles. And so I'm just going to draw 2 dots in there because the number of particles are staying the same. And it also doesn't say anything about me changing the temperature, so therefore I'm just going to draw the particles moving at 2 speed. Finally, I'm down here now. My volume is very, very large compared to what it was, but my pressure is very, very small, so my drawing should show, let me draw it real quick without it being completely weird. Boom. So I've got a much bigger volume because I've got a bigger box. And then I'm just going to put those 2 particles in there. 1, 2, and again my temperature will be the same. So now, just by looking at these particle diagrams along with this graph, I clearly see that my volume is increasing as I go along the x-axis. That's why I drew bigger boxes. My number of particles and the temperature stay the same. That's why I kept number of particles and the speed of the particles the same. Now the pressure is decreasing. And the reason that happens is because if you imagine taking 20 people and putting them in a very tiny closet, it's going to get pretty uncomfortable because of the amount of collisions. But if you were to take those 20 people and put them in a gymnasium, like over here, they're hardly going to bump into each other. Therefore the pressure will be very, very small. So here's your assignment. I just walked you through Boyle's law in which you compare pressure and volume. What I want you to do is I want you to draw particle diagrams for the following. P, N, and then if you remember those guys are directly proportional, you're going to pick 3 points. One here, call that point 1, this point 2, this point 3, and I want you to draw particle diagrams. Now remember, the temperature in this case should be the same, and the volume should be the same. So you're just changing the number of particles. The final one that I want you to do is this. You've got pressure, and you've got temperature, and remember the temperature in order for it to be directly proportional has to be in Kelvin. I'm just going to pick a few points on there. Point 1, point 2, point 3. I've got those 3 points. Now you guys are going to draw particle diagrams for this, this, and this. Make sure you're comparing, and then particle diagrams for this, this, and this, in which you're comparing pressure and temperature. Now at the beginning of class next time, we're going to talk about these, so make sure that they are done and ready to go. Please contact me with questions, and you will have time to come to a study group tonight. If you do have time, please come to the study group tonight. It will be at 6 o'clock. I'll open the north door of the science building. You can come in and ask me questions. Other than that, make sure you're working on your lab report because it is due next time, and I posted a review on Google Classroom. Make sure you go through that. Again, please email me with questions or let me know if you're having any problems. Good luck.